Okay, good morning everybody. So let's take a look at our pre-lab questions here. Well, I guess it could be morning, afternoon, or evening, depending on when you're watching this. So we're going to do the pre-lab questions for our first lab on percent composition here. So here's the purpose. So over the next few days, we're going to continue our exploration of analytical chemistry techniques. So previously, we just looked at our first, what I would consider analytical chemistry technique, and that's determining the moles of a gas using volume. So today we're going to do a second big analytical technique. So recall these are techniques in which elemental structures or properties of a chemical compound are analyzed numerically. So for our first technique, we analyzed chemical reactions based on gases, and we used Avogadro's law for that. So today's technique will include two new experimental techniques as we pursue our analysis of a compound based on percent composition. So every chemical substance contains different elements in different quantities. That means that no two chemical substances will consist of the same percent composition. If known, this percentage makeup can be used to identify unknown substances, as Detective Harrison Hoyt had learned. So this investigation will begin with some pre-lab questions. So this is a rather complex lab, and that requires that we break down our more complex questions into simpler to answer parts. So remember, anytime we're presented with something that's complex, we need to answer a question or a problem that's complex. We want to take that question and see if we can break it apart into simpler questions that we can then use the answers to those simpler questions to build up to the answer to the complex one. Okay, so here's our objectives. We're going to use chemistry technique number 2, analysis technique 2, percent composition, to determine the correct mass percent of each element in 0.00500 moles of lead to iodide. We're going to analyze a potential chemical reaction utilizing your understanding of conservation of mass, chemical equations, classifications, chemical formulas, mole ratios, and algorithm programming. So we want to use this stuff for the purpose of constructing a knowledgeable hypothesis. So this is what the purpose of the pre-lab questions are. We need to build up our hypothesis base. So again, we don't just take random guesses here. It's not an educated guess for our hypothesis. It's a knowledgeable prediction. So we also want to practice these two chemistry techniques, so decanting a liquid and quantitative filtering. So this is a very, like I said, it's a very technical lab, but it's fun to do. So here we'll start with these pre-lab questions. Conservation of mass. So to start us off, we need to examine the chemical recipe for this reaction in order to get to what we desire, a knowledgeable prediction as to the answer of the experimental question. So recall, we don't do guesses here. So we can't know anything about percent composition of a substance if we don't know what elements make up the compound. So we do have to know what elements we have in order to determine a percent composition. So thus we need to help with our recipe. So to get the hemp seed oil flowing in our brains, we're going to recollect our knowledge of conservation of mass. So I'm going to let you answer this one here. So as we go along in the pre-lab questions, some of these I'm going to have you answer. So it's questions that we should know the answer to at this point. So these are ones that you're going to answer and I'll check off. Okay? So you should know what the law of conservation of mass states. So describe how it allows you to predict this. We should know this. So we did this in the pre-lab questions for our last lab there. Okay, so we got those. So having said that, let's take a look at today's reaction. So this is today's reaction. So here we have, this is our first reactant, and it's made up of, remember, when we look at chemical reactions, chemical products, reactants, when we look at any type of chemical substance, we need to know what elements make it up, right? So in order to know percent composition, we have to know what elements we have. So remember that when we look at this, we have 1, 2, 3, 4 letters here, right? But it's not 4 elements. How do we know when one element ends and another one begins? And we look for the lowercase letters. So here we have a capital P and a lowercase b. That means this is one element. So that's one element. Then we have a capital N. That means we've now moved on to another element. And there's a capital O, so this is a separate element. So this particular chemical substance is made of 1, 2, 3 different elements, P, B, N, and O. Okay, so here I've represented this down here. Now in this case, this N and O are bonded together. So I just represented this NO as this blank circle here. So this is actually red in color. So I'm going to get my colors out so you can't see it on the printer here, but that's if we looked at the color sheet. So you want to look at the color sheet in your notes, that's red. So this is NO3. So that's my blank one there. So my red dot, I'm going to come over here. So this is my PB. Okay, now I have, let me get a different color. So we got black over here. So these are black circles. This is my NO3. And again, you'd see that on the color ones. Then we also have green and we have blue over here. So green and blue. So this is going to be green. So if we look at this element over here, the next reactant is made up of a capital K, we have a capital I. That means that these are individual elements. So this substance is made up of a K and an I. So we'll say, I can't remember, I don't have the color one in front of me. We'll say the triangle is the K. And then the I we'll say is blue, I don't remember. It's either this or it's switched. I might have switched it. Don't yell at me if I switched it. Okay, so the box then we'll say is blue, and that will be our I. Okay, so here's our two reactants. So we have PbNO3 is one reactant, and this is called lead nitrate. And the second ingredient in the recipe is K&I, which is potassium and iodine. So this is potassium iodide. Okay, so just like in the last lab, I've given you one of the products, and I've asked you what the other product is going to be. So I need to know what goes here, what's the other product going to be made of, and how many will I have. So this is what we're going to use the law of conservation of mass for. So if we look over here, one of the products that I gave you was made up of the K's. So the K is my green triangles. Right, and it's made up of NO3. So each of these individual compounds consists of one K. So there's my 1K and one NO3. So if I go back and use the law of conservation of mass, I see that I began with 2 potassium atoms. Right? So notice here I don't have anything in there. So that's where we're going to go in there and write down what we have. So Ki, how many Ki's did this recipe call for? 1, 2. So it called for 2 Ki's. So I began, law of conservation of mass again states that whatever you begin with, you have to end with. So in the beginning, I started with 2 triangles. So 2 potassium atoms. That means I had to end with 2 triangles. So this particular compound here comes in a ratio of 1 to 1. 1 potassium atom to 1 NO3 atom. And again, in a few weeks we'll learn why this ratio is what it is. But this is the way it is. This particular chemical substance is made of only 1 potassium atom and 1 nitrate molecule. Okay, but so I couldn't just have one here. Right, I couldn't just draw 1 triangle and 1 circle. That's because I started with 2 triangles, so I have to add another one. The only way to add another triangle is to also add another circle. So I needed 2 of these in order to conform to the law of conservation of mass. And I see that that works because I started with 2 circles here, 2 nitrate molecules. So that means I needed to end with 2, and there they are. Okay, so now I can come in here and I can cross some stuff out. So I've gotten rid of 2 triangles and 2 circles, so these are gone. So what does that leave me with? So what is left must be what this compound is made of. So I see that I'm left with a red circle, and I'm left with 2 blue boxes. Okay, so that means this is what my product is going to be. But how many will I have? So let's just start by adding 1. So these must be bonded together because I see here I have only one product missing. So that means these things all must be connected. Right, so let's see. So I need to start with one circle, one red circle here. So now I have to decide, do I add one blue box or two blue boxes to this? So let's add one blue box to this. Boop, boop. Blue box. So we'll put that in there. So now I can come back here and I'm going to cross this out. So I've used my one red circle and I've used one of these blue boxes. I still have this one left. So the question is, can I just add another blue box down here? Maybe I'll just add another blue box. Like that. Is this correct? So I have one red circle and I have two blue boxes. But this is not correct because these two are not connected. That means what I have showing here in my picture are two different products. I have one product that's made of PB and I, so PBI, and then I have another I. If I did this, what my reaction would look like here is PBI plus I plus, then I can come up here, 2KNO3. So this would give me three products, but I don't have three products here, I only have two. So that means this can't go here. So this is not right. Can't do that. So, in that case, where must this blue box go? The only thing that I can do is to attach it to this. So now I can cross this out. So this is my one product. So now I write the chemical formula in here. So what is the what's the ratio of PB to I in my product? So I look at my picture. I have one PB. So I'm going to write that down. Again, you can put a little 1 down there if you want. And now my other element is I, and I see I have two of them. So I'm going to put a 2 there. PBI. Okay. So now I just count, I have to put my coefficient in here. So how many of these PBIs did I need in order to conform to the law of conservation of mass? And I see here I only needed 1. So again, you can put a 1 there or you can leave a blank. So there we go. So these are the two products that will be produced in this chemical reaction that we're going to study. Alright, so let's use this now to answer some questions. So what do we know? What does this tell us? So these questions are going to be looking at all the information it tells us. So, using your understanding of the law of conservation of mass, we're going to send Dr. Cook to culinary school. So chemical equations and mole ratios. Question 3, what elements make up the final product? So justify your answer with knowledge. So what elements make up the final products? So what elements? We have the same elements that we began with. So the final products are made up of PB, NO3, KNI. And why do I know that? So the law of conservation of mass So the law of conservation of mass states you end with what you begin with. Smush that in there. This is why I like writing on documents. So you end with what you began with. So draw a diagram using the correct symbols. So we did that one already. Boop. Number 5, how many moles of this product did we need in order to balance the equation to conform to the law of conservation of mass? So how many moles of PBI2 did we need? So we only needed 1 mole in order to match up all of the different shapes. So here I only needed 1. So what's the value of the coefficient you'll place in front of this substance? So we just needed 1. So now the coup de grace. What is the correct chemical formula for this compound? The ratio of the elements within the compound is the correct chemical formula. This is what's known as a chemical formula. So the correct chemical formula is I needed 1 Pb atom and I needed 2 iodine atoms. So there's the correct chemical formula. So let's look at question 8. Examine the following chemical formula here. So using your current understanding, so I'm going to do this one, using current understanding, describe what this formula is telling you. So again, I'm going to have you do that one. So let's look back in question 10, and let's look back to the full chemical reaction up there. So examining the full chemical reaction closely, what classification of reaction is this? So what is going on? So again, I'm going to have you do that. So this is it synthesis, is it decomposition, combustion, single replacement, double replacement? What is the classification of reaction there? 11, lead iodide is unique among the 4 compounds involved in this for one big reason. So this substance is unique compared to these 4. What's different about it? So look through the chemical equation here. What do you think makes this substance different than the other 3? So the other 3 are the same in some way that this one is not. So see if you can find the pattern in there. Okay, so you'll do that. So what you noticed above is the reason double replacement reactions take place. So there has to be a change in the state of matter. So there has to be a change in the state of matter of one of the compounds for this type of reaction to happen. So what you'll see in this lab is the formation of what's called a precipitate. So you're going to see the formation of a precipitate. What is a precipitate? A precipitate is a solid that forms from 2 liquids. So it forms from a pair of aqueous compounds. I'm going to just abbreviate. So a precipitate is a solid. So the key is when you mix 2 liquids together, so 2 chemical substances are in the aqueous state, a solid forms. So aside from a solid, what other state of matter change could result in a double replacement reaction? So you could also see a gas that forms. So, or we could have a liquid that forms. So we could have a gas or a liquid that forms. So hey chef, Cook just dropped some knowledge on you right there. So let's take a look at the next group. So now we're going to look at the actual percent composition part. So with chemical formulas to look at now, let's hit the math that will allow us to develop a proper hypothesis. So question 14, describe in words what the concept of percent composition of a substance tells you. So I'll let you do that. Describe mathematically percent composition. Mathematically, this is our mathematical equation. So here the percent is the mass of a single element divided by the mass of the compound. So the mass of the whole. And then to turn it into a percentage, we multiply by 100. So what 3 numerical properties are involved in percent composition? So we need the mass of the element, the mass of the compound, and the percent composition. So these are the numerical properties that we have here. 17, how many different forms of the equation are there? We have 3 different variables. So this equation has 3 variables. So that means we have 3 different versions. We have 3 different versions of this equation. So we can rearrange this to solve for 3 different parts. So 18, solve the base equation for the other 2 variables by canceling out everything using your algebra skills. So we'll do this together. So right now the equation is, as written, is solved for percent composition. I also want the version of the equation that is solved for mass and that's solved for the mass of the whole compound. So we want to do all of those together. So we're going to get our sheet of paper out, and we're going to use some algebra skills here. So again, here's the base equation. So percent so the mass of the element divided by mass of the compound times 100. So because I have a fraction here, I'm going to write these other two parts in fraction form too. So remember, we do that just to make everything the same within the equation. So in this case, let's say I want to solve for the mass of the element. So this is my x. That means I need to cancel out what's around it. Right now I need to cancel this out and I need to cancel this out. So this is where the fraction part comes in. So we just go about canceling out what's around my x by doing the opposite of what it's asking. So let's get rid of the 100 first. So we'll get this out of here. So to cancel this 100 out, I just need to move the 100 from the numerator there to the denominator. And then that will cancel. So remember, you can do whatever you want as long as you do it to the other side too. Whoops. So 1 over 100. So now again, before I cancel anything else out, I'm going to go ahead and rearrange this. I'm going to go ahead and rewrite the equation. So I'll multiply across. So over here I have 1 times percentage. So percent on the top, and on the bottom 100 times 1 is 100. And then over here I have the mass of the element. And on the bottom I have mass of compound. And over here I have 100 times 1 is 100, and 1 times 100 is 100. So 100 divided by 100 is 1. So this is my equation that I have left now. So is my x by itself yet? And I see that it's not. So I have to cancel this out. So again, because it's in fraction form here, all I have to do here, it's in the, what I need to get rid of is in the denominator. I'll just put it in the numerator. So mass of compound up top over 1, and again I can do that. I didn't leave myself any room. I'll have to abbreviate compound over 1. So mass of compound over 1. So now I just multiply across, and over here now we have mass of the compound times percentage. So we can't multiply letters together. So I'm just going to put it in parentheses. So that's going to be times the percentage. And on the bottom I have 1 times 100 is 100. And over here I have the mass of the element. On the top times the mass of the compound. And then mass of compound times 1 over here. I'm going to add that. Okay, so there again, mass of compound divided by mass of compound just cancels out. It's the same thing. So just like 100 divided by 100, these two are both the same thing. These two are both the same, so it cancels out. Now I have the mass of the element by itself. So the equation that I need here, and I always rewrite it. So I'm going to take the mass of the compound times whatever my percent divided by 100 equals the mass of the element. So there's my equation. So I'll go ahead and put this back in here. So there's one of my equations. Put it here. So I'm going to let you do the second one. So ballin', or something like that, whatever you could say nowadays. So we just found the three forms of the equation we need to use for this lab. So question 19, you would go over to your spreadsheet if you want and plug that in, or you can do it by hand. So now for the rubber and road slapping. So how are we going to experimentally determine the percent composition of lead iodide? So we want to know the percent composition of lead and iodine in this substance. So we need these concepts. So we need to know the mass of lead, the total mass of the PBI sample, and the total mass of the iodine. So again, if we look at percent composition, that's what we need. We need the mass of the element and we need the mass of the compound that we're looking for. So recall, we're going to be filtering out this precipitant. So what you have here, if we go back to the equation, the lead iodide, what's going to allow us to analyze the lead iodide is the fact that it's in a solid form. That means we can filter it out. The rest of this is going to be dissolved in water. So if you run it through a coffee filter, it will just run right through the filter and this will get trapped. So we can get the mass of this thing. So that's what the purpose of this lab is about here. So question number 20. So what do you think that precipitate is? Again, I'll let you answer that. So what is one of the three measurements we will know? So when you filter out the lead iodide, what you're going to know is the total mass of lead iodide in the sample. So if we go back to the equation here, you're going to know the mass of the compound. Okay, so the other measurements we will use the mass of lead 2 present. So here we're going to do what my mama told me to do, or told me not to do, and that's to make an assumption. So let's work through a few questions here to determine what that assumption is that's going to be made. So looking at our materials list, we see that this lab calls for 0.0050 moles of lead nitrate. This is where your lead is coming from. It's coming from this compound. Lead is a solid, it's a metal though, so we can't just take a chunk of metal and drop it in water for this reaction. It had to come in a different form. Again, we'll talk later in the year about what that form is, what this means. But this is where it's coming from. So the original, one of the original reactants, this reactant that you're going to put in, we don't care about this. This is the only reason that this is here is it makes the lead soluble in water. So it allows us to take these lead atoms and put them in a dissolved state. So let's look at question 22. We need to determine how much lead we have in here. So we know how many moles of PbNO3 we have. So remember, anytime we know moles of something, we can find mass of something, right? But I don't care about the mass of the whole thing. I just want to know what the mass of the lead is. What part does that make up? So look at question 22. What mass of lead 2 nitrate will give you the desired 0.0050 moles of lead? So I'm going to let you do this. This is a conversion question. So remember, we need to convert. So you're going to start by, I'll start you out here. So convert, and then we're going to take what we know. So I want 0.00500 moles of PbNO3. So that's what I don't want. I want to take that and convert it into grams of PbNO3. Okay, so then you would go on about that here. So what is the percent composition of lead and lead nitrate? So again, I'm going to have you do this one. So here we just go back up to the formula. You're searching for this. So again, I'll get you started. So remember, here we go to the math steps. So what is step 1? We circle what's missing. So percent composition of lead is missing. And then step 2 is to underline the values that we know. So we're going to go back up to this question here. So what do you know? You're going to know the mass. So whatever your mass number is. Step 3 is now to list stuff out. So if we go to a sheet of paper here, you could list out, again, I'm going to start choosing, the first thing you list out is your X, and we want, wait, what is this question? So, sorry, not mass. So this is the percent of lead. So that's what you want. And again, now you list out what you know. So you're going to know, put here, I'm not going to tell you what the mass is, but this will be, you're going to know this here, and actually this one, no, we will do this one. So let me get another sheet of paper out. So let's take a look here. So here we are going to put this down. Find a blank sheet of paper. So again, we want to know the percent of lead in lead iodide. So there's step number 3. So your X is the percentage of lead in PbNO3. Okay, so what do we know here? In order to do that, we need, so in order to do this, we need to get, here you're not given any numbers. So what that means is, to get the percent composition of lead, we need to get the mass of this substance. So what's the total mass of this substance, and what's the total mass of the parts? So my percent composition equation is equal to the mass of the element divided by the mass of the compound times 100. So we need to know the mass of the element. So this is where we have an issue, right? So this is where I was briefly confused, since I haven't looked at this in a year. What I wrote, my mistake. You're free to call me out on that. So here, I didn't give you this, right? So the only thing that you know is this. So you have to ask yourself, we skip down, we list out what we know, we label it. We don't have anything, so then this is where the checking off comes from. In order to solve this question, this is my X, I'm going to check stuff off. I need this and I need this, but I don't have this listed, so I have to ask myself, well shoot, did I miss something in the question? So let's go back and look at the question here. What is the percent composition of lead and lead nitrate? No, I didn't miss anything. There are no numbers at all there. So where does this come from? This comes from our periodic table. So if you're not given the mass, if we just want to know the mass percent of this stuff, we go to the periodic table. So we're going to make a little table here, or you can go to Excel if you were able to do this. So here's our Excel chart. So I'm going to list out my elements. So here's the table we've been using. So elements, and then mass, and then the number that I have. So I'm going to multiply that. And then over here you have the total mass of that particular element. And then we're going to add all those up. Okay, so what elements make up this substance? So we have Pb, capital N, capital O. So we're going to go to the periodic table and find the masses there. So Pb has a mass of 207.2. So 1 mole of PB has a mass of 207.2 grams. And how many do I have in my chemical substance? So I just see 1 here. So I multiply those two together, 207.1. Okay, how about N? So this is where we have to pay attention. So remember, there's parentheses around this NO3 for a reason. And that's because it means you have 2 of these NO3 substances. So just like in math, if you see parentheses, it gets distributed in. So within the substance here, I have only a single nitrogen. But I have 2, so 2 times 1 is 2. So I'm going to have 2 nitrogens here. Let's see what the mass is. So we find nitrogen, 14.007. And then oxygen, we have 15.999. How many oxygens do I have here? So again, I look at the substance. Each nitrate molecule, each NO3 molecule, has 3 oxygens in it. But I have 2 of the whole thing, so 2 times 3 is 6. So I have to multiply these out. So that's 28.014. 4. And I'm going to go ahead and grab the calculator for this one. So we'll come over, calculator, 15.999 times 6, and we have 95.994. And we never round anything in the middle of a calculation. So now we're going to go ahead and add these up. So the total mass of the compound. And again, if you're doing this in the spreadsheet, this would just be the sum here. So that plus 207.1 plus 28.014. So 331.108. So 331. Remember, when we add significant figures, we have to round. We're only looking at the number of decimal points. So we want the fewest number of decimal points. So in this number, I have only a single decimal. Here I have 3 decimal points. Here I have 3. So I can only use 1. So that means this number has to be rounded to only the 10th spot. So this is the only decimal point I can put down. So I look behind, I see a 0, so it gets left there. So there's the total mass of this substance. 1 mole of lead nitrate will have a mass of 331.1 grams. That's why we're not using 1 mole of it here. So we'll go back to our sheet. Oops, there it is. And I'm going to add this to the list. 31.1 grams. It's my total mass. So now I can check this off. I have this part of the equation. But what about the mass of the element? What element am I looking for? This is why it's so important you put labels on. PB. Can I get the mass of PB? Well, yes, I can. I just go and I get it off the periodic table. Right? That's what you have right here. So it turns out you do have this mass too, 207.1 grams. And that's the mass of PB. So now I have everything I need. So step 9 is we just plug this stuff in. So I'm going to come here. So X is equal to 207.1 grams divided by 331.1 grams times 100, and our grams cancels out. Again, percentages are always unitless. There's no units on percentages. So clear that. So 207.1 divided by 331.1. So 6.625 blah 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 times 100. So 62.549 blah blah. So we have to know where to cut it off. So again, what digit do I cut it on? So now we're doing multiplying, dividing. So that means I'm looking at the total digits, not just the decimal points. So here I have 1, 2, 3, 4 digits. 1, 2, 3, 4. So that means my answer can have 4 digits. 1, 2, 3, 4. So this 4 is this spot. The 100th spot is the last spot I can write down. So look behind it. I see a 9. This means this gets bumped to 5. So 62.55% lead. So by mass, this lead nitrate substance is made up of 62.55% lead. So we can go and write that down here. 62.55%. So using your question 24, using your answer to the previous two questions, what is the beginning mass of lead that will go into this reaction? So now, again, we follow the mass steps. Step 1, circle what's missing. Step 2 is underline what you know. So what you're going to know now is the mass percent of lead in this substance, and you're also going to know the mass that we're actually starting with. So again, we're not starting with 1 mole of lead here. We don't have 331.1 grams, so that means we won't have 207 grams of lead. We're starting with only 0.0050 moles of lead. So we need to know the mass. So for example, let's just say that this is 1 gram. So 0.005 moles of lead is the same as 1 gram of lead. If you had 1 gram of lead, what this question is asking, if you had 1 gram of lead nitrate, of that 1 gram, what mass would be lead? So 62.55% of the 1 gram would be lead, or you would have 0.6255 grams of lead. How do I know what to do here, though? Well, we go back to these equations. So here, you have a percent composition, but we're solving for a different part. You're solving for the mass of the element now. So we would use this version of the equation. The mass of the compound, that's what you get from the 0.005 moles. We know the percentage, 62.55%, so we can plug that in. So again, I'm going to let you do this one. So what does the law of conservation of mass tell you about the quantity of lead you will have after the reaction is complete? So if I started with, so again, my example, this is not what you actually have, but if I started with 0.6255 grams of lead in my substance to begin with, that means my ending substance, my ending chemical quantity of lead would also be 0.6255 grams. Right, so I'll let you do that one, and here's the end. So last couple questions. So here we are at the end now. We've come to the conclusion of this. So far too late, I know. So propose a hypothesis as to what you think the assumption is that we're going to run with. So I'm going to give you a hint here. Well, not give you a hint, we'll talk about this. We're going to assume that all of the lead you began with ends up in the chemical substance, in the lead iodide. So we're going to assume that we don't lose any of the lead atoms as the reaction goes along. So whatever quantity you begin with, we're going to assume we end with here. Okay? So, long streaks of rubber have been laid down. So now we can do 7. What is the predicted chemical formula for lead iodide? Again, we looked at that. So we predicted the chemical formula to be PbI2, and we predicted that based on the law of conservation of mass in our boxes there. So using your predicted chemical formula from the balanced chemical equation, calculate the percent composition of lead. So again, mass steps, we want to know what the percent composition of lead is in this chemical substance. So we're using the same process here. We're just, instead of lead nitrate, you're doing lead iodide. So I'll let you guys do that one. So assuming that all of the lead combined, so there's our assumption, with the iodine, what is your predicted mass of lead? And now you can write your hypothesis. So then 31, describe how you will calculate the measured percent composition of lead iodide at the end of this experiment. So what measurements will you have to take? So this is your experimental setup. So we'll think about that there. Okay, so good stuff. We should be about ready for the experiment now.